It's a major technical problem sometimes when you're building circuits that your transistors get too hot, and you think if we went from 2 transistors to 4 transistors and spread the current out, it might not get as hot. And let's try to go through one of those circuits right now and see how it works. We've got a flyback driver circuit here, fairly standard, with 2 transistors here and here, a primary coil, a feedback coil, and a secondary coil. And the primary coil here, 6 turns in red. Secondary coil, the feedback coil, 3 turns in white. Secondary coil, 2,000 turns in black. And what happens is this feedback coil flip-flops 20,000 times per second, and it goes in the base of that transistor and flips them on or off very quickly. So it really works quite nicely to make wireless power, but it gets too hot. Let's see how that works. Here we are now at 10 volts and 4 amps. It's flipping 20,000 times per second, 20 kilohertz, and it's making wireless power. The black coil, as you can see, that there's a light bulb coming on, that's coming out of this 2,000 turn coil. So everything's working quite nicely. The trouble is these 2 transistors will get hot very quickly at 4 amps. That one's hot. That one's hot. They're both getting hot. So if we could take that 4 amps, and instead of having 2 amps go through each transistor, we only had 1 amp, it might stay cooler. Let's try that next. Okay, now I've got the same circuit, this flyback driver circuit, with the primary coil 6 turns, feedback 3 turns, and secondary coil 2,000 turns, making wireless power and hooked up to a multimeter so we can read frequency. But instead of just 2 transistors for 0 current switching, I've arranged 4, 2 on one side in parallel and 2 on the other side in parallel, so we got 4 transistors in total. Let's turn on the current and see what happens to power. Now we're at 10 volts, 4 amps just as before, 20 kilovolts just as before, and we're making wireless power just as before. And the question is now, how are these transistors going to heat up? Is it going to make it smooth out the heat, or is there some other trouble? Let's just put our finger here to see what happens. So far, so good. Nothing's really burning. We're at 4 amps, 9 volts. I'm keeping it down just for safety to 4 amps. Not too hot. A little warm. Pretty warm. Not warm at all. Give it a few more seconds and I'll turn it off and we'll see how hot everything is. Okay, let's turn it off now and see how hot everything is. Cold, hot, hot, cold. So what's happened is the 2 central ones are hot, the 2 outside ones are cold. So we haven't really distributed the current yet. Let's do another trick to see if we can make it more even. What I've done next now is I've taken a 1 ohm 50 watt or 100 watt resistor and put it just above the input to the hotter transistors, the 2 inside ones, and left the other 2 outside ones alone. Let's turn on the power again and see what happens. Let's go right up to 10 volts, 3 watts, the same power as before. We got the same wireless power, the same everything. Now we get a little higher on the current and voltage because the resistors, but everything's set the same, 11 volts, 4 amps, and let's see how the heat distributes itself among these transistors as we leave them on for a little while. There's you see there's a little resistor there, 1 ohm and 1 ohm on the 2 inside transistors, but not on the 2 outside. Let's feel how hot they are. Nothing's hot yet. That one's getting hotter now, so it's definitely working over here a bit. Let's just let them run for a few seconds, see what happens. We're getting wireless power the whole time here at 21 kilohertz. That one's heating up a little more. That was not as hot. That one's not as hot. That was a bit warmer. So we've distributed it a bit. Wait a few more minutes and just see how hot they get at 11 volts, 4 amps. We'd like to be putting 1 amp through each transistor rather than 2, because we have 4 of them now. This is running transistors in parallel, which is always difficult. What I'm trying to do is use a little 1 ohm resistor, 50 watt input, just the hotter ones, and balance them that way. A little balancing act, just like you'd handicap horses. That one's getting warm, the outside one now. It's not too hot now, it's still getting pretty hot. That one's not too hot now. It's definitely getting balanced more than before. So this seems to work, putting a 1 ohm. You could also add a half ohm or a 2 ohm resistor. But I'm waiting to see if any of these two things get too hot before I add any more resistance. I haven't actually made that determination yet. Tell you what, let's turn it off and feel how hot these transistors are now. Warm. Very warm inside. That one hasn't gone down enough. Warm. Warm. So this is the only one that's still a little bit hot. We can put a little more resistor there and see what happens, like 2 ohms. Okay, now I've adjusted it for 0 ohms, 2 ohms. I'll put 2 1 ohm in series, 1 ohm and 0 ohms. Let's turn the power on again and see what happens. 11 volts. Lights on. Let's see now how that affects it. The only one getting hot before was this one. But now I've put 2 ohms on it, and let's see if that balances it out. And this enables us to run the circuit a bit higher. That's definitely not overheating, that one. Not overheating anymore since I put the 2 ohm resistor on it. That one's okay. And that one's okay. So right now at 0 to 0 ohms, added in series just above the red collector, these transistors are all heating about the same way. This is like handicapping horses. You put the fastest horse, you put the most weight on. The lightest horse, you don't put any weight, and you try to make them all get to the finish line at the same time. This is for a flyback driver circuit. With 2 transistors, we've gone to 4. A little ferrite coil transformer with a primary coil, a feedback coil, and a secondary coil, all of which are working by 0 current switching. Let's try now, see how hot they are. Warm. Not too hot. Warm and warm. So this technique, very simple, definitely works to some extent. When we have transistors in parallel, we can put very small resistors like 1 ohm, 50 watt, because the transistor is going to get hot, the resistor is going to get hot just above it, and that way we can adjust how much current goes through each one. Here's the transistor. Okay, we're at 11 volts, 4 amps. Let's turn that off and feel how hot everything is. Warm. Medium is not too bad. That's got 2 ohms on it now. Warm with 1 ohm and warm. So this is not a miraculous technique, but if we want to put 4 transistors in parallel, it's certainly a little good technical trick to follow. It's difficult to get all the transistors to fire at the same time, and we've simply put some resistors here on 1 ohm, 50 watt on heat sinks, because they're going to get warm, take all the heat. And that way we can run, that one's quite hot. But it doesn't matter, it's a resistor. That way we can run 4 transistors rather than 2 and get twice as much power out of the circuit. Thank you very much. Now another common problem when making circuits is that you use MOSFETs like these, and they get too hot, even hiss. You can hear them breaking down with the current or voltage gets to be too much. And here we have 2 of them together flipping back and forth by what's called 0 volt switching. and there's a transformer over here which controls it. Let's see how this circuit works. We have what's called a flyback driver, where we have two MOSFETs like this attached to a primary coil that's tapped in the middle, and they flip on and off alternately 20,000 times per second due to this wiring over here, which is well known, and they excite the secondary coil here over 2,000 turns. And here's your primary coil of about 8 turns tapped in the middle and 2,000 turns. Now what happens is, when we start to put on some power, let's watch what happens. 4 volts. MOSFETs aren't on yet. Now they start to turn on about 6 volts. And you can see the current's picking up. We can go to 9 volts quite easily in about 3 amps. And you can see the lights just starting to shine, 21 kilohertz. What happens, however, when we go a bit higher, you hear it 10 volts. This one's starting to hiss. If you listen very carefully, you can hear a high frequency sound even though the light's brighter. So without wishing to break it, we're going to turn this off and try to use 4 MOSFETs rather than 2 to get more power. Okay, now we have 2 MOSFETs wired in parallel here and 2 wired in parallel here. We have 4 total, the same frequency, 20 kilohertz, and a somewhat brighter light because we've got 12 volts and 4 amps. We could only get to 9 or 10 amps before. So what we're going to do here, we're just going to wait a while for a few minutes and see if these things all get hot together in the same way, or some get hot before the others. Okay, we're putting 11 volts, 5 amps, and 50 watts to all 4 of these MOSFETs together. This one was staying cool. This was getting a bit warm, so I've put a 0.5 ohm resistor on it, 50 watt power. This one was getting the hottest. I've got a 1 ohm resistor, and this one was cool. So let's just follow all 4 of those and see if I have to adjust it further. The wireless power is still coming out quite nicely. We have 50 watts going through here at 21 kilohertz. Wait a minute now, I'll see what gets hot. Okay, I've left it on for about 10 minutes. The highest sustainable temperature we can get is about 8.5 volts, 3.5 amps, 30 watts, 0 ohms, 0.5 ohms, 1 ohm, 0 ohms for the resistors in each MOSFET. And this way we can adjust all the MOSFETs to about the same temperature, 20 kilohertz, and some wireless power coming out. They're all about the same temperature. Warm, 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 warm. So none of the MOSFETs are overheating. The resistors, of course, getting a bit warm, 1 ohm and 0.5 ohm. So this is an interesting way. If you do use 4 MOSFETs in parallel, you can put very small resistors of like 50 watt, 0.5 or 1 ohm, and you can adjust the MOSFETs so they each carry about the same current load. An interesting technical device. Thank you very much. We continue.